Well, thank you. I'm Ken Sandhage in the School of Materials Engineering here at Purdue University, and I'll be telling you today about our toughened low-cost ceramic parts for ultra-high temperature components. There's ever-increasing demand for higher efficiency and performance in systems that require higher temperature materials for lower cost electricity, fuel-efficient aircraft, higher performance rockets, and manufacturing. And in particular, today I'll talk about Frictionstir welding tools. So the upper two panels show two electricity generating systems, concentrated solar power on the left, combined cycle gas power plant on the right. For both of these systems, we need higher temperature materials for the heat exchangers, the turbines, and the receivers to operate more efficiently to create lower cost electricity. The bottom two panels show defense applications. The one on the right shows automobile manufacturing. And for these, again, we need higher temperature materials for heat exchangers for more efficient engines, higher temperature rocket nozzle components, and higher temperature tools for Frictionstir welding. And so advanced steels, nickel-based superalloys, and other structural metal alloys are currently at their high temperature limits. So we need materials that are more mechanically robust than structural metal alloys to achieve the higher temperatures. And we believe that the solution is our Netshape toughened high temperature ceramic composites. An example of which is shown here. And so on the left you see a schematic of two metals placed together with a Frictionstir welding tool in between. What happens is the tool goes in between the metals and through friction heats up the metals. And so Frictionstir welding is a solid state non-melting technique for joining metals. You stir the soft metal into itself. Defects are avoided because you're not melting the metal, and higher strength, thinner welds are therefore produced. Now currently, low-cost steel tools work just fine for soft metal alloys like aluminum alloys, but if you want to join high-strength steel, superalloys, and titanium alloys, the current tools, tungsten rhenium, polycrystalline cubic boron nitride, either erode or fracture, and they're very expensive. And so here's a table kind of illustrating this. Hardened steel works fine, it's low cost for low temperature metals. It doesn't work at high temperatures. Tungsten rhenium alloys are very high melting, they're quite fracture resistant, but they erode too quickly and they're expensive. Polycrystalline cubic boron nitride is diamond-like, so it's very erosion resistant, but it's almost diamond-like in cost as well, and it's not very fracture tough. So our material satisfies all these requirements, and we filed IP on this, and we have a startup company, XMAT, that's making these tools for testing. So conservatively, estimating the cost of our tools instead of thousands of dollars a piece, they're more like 50 bucks or less. We're also making components for high temperature heat exchangers for electricity generation, as I mentioned earlier. For example, we can make these toughened ceramic composite heat exchanger plates. The drive here is to have higher cycle efficiency by operating the turbine at higher temperatures with a higher temperature heat exchanger. And so right now metals are limited to about 550 degrees C. If we can shove the temperature to 800 C or higher, the efficiencies go up significantly on the order of 19% or more, so we have 19% lower cost electricity. So with that, if you have other high temperature material needs, certainly contact me. If you are interested in licensing or commercialization of this approach, please contact William Buchanan at the Purdue Research Foundation. Thank you very much.